Good afternoon. Chandan, ready?
Yes.
Okay, so let me, it's 4, I think we can start. Okay, so welcome again to all of you. So it's a pleasure to have today Chandan Setty from University of Florida, who will tell us about the instability of Luttinger models, surfaces, and SYK models. So just before giving you the floor, just let me remind everyone that you are all muted, but you can unmute yourselves and ask questions whenever you want. So thanks, Chandan, a lot for agreeing to give the talk, and please start whenever you want.
Okay, I'd like to thank the organizers for this opportunity. So today I want to talk a little bit about this following topic, which is studying instabilities of Luttinger surfaces. And I'll tell you what these surfaces are, but I want to try and make connection with SYK type models. This talk is going to be predominantly from condensed matter perspective. And really the purpose is to try and get maybe some of you who do holography a little bit more interested in these topics, and maybe try to make connection with models of holography. So I'm not really going to go into the holographic aspects in terms of writing the models per se, but hopefully at the end of this talk, I'll convince you that maybe there is something more to learn about Luttinger surfaces and how one can make connections with models of gravity. Now, I'm not an expert in holography per se, so if I use the word ADS and if I don't make sense, it's quite a possibility. But you guys can chip in whenever you want. Feel free to stop me. I may be using some terminology which may be sometimes new to you. And if that's the case, feel free to interrupt me. So much of this work is going to be, it's going to be out soon, within a few days probably. And the second part is some work that's in preparation. Okay, so first of all, what are Luttinger surfaces? So we are all familiar with the concept of a Fermi surface. A Fermi surface is a contour of poles of the Green's function. So you have some Green's function. It looks like this, where this is some single particle dispersion, and you have some interactions in the problem, and those interactions are captured in the self energy. Now, in the simple case where the self energy is very small or close to zero, one can define a Fermi surface, which is basically the contour where the Green's function diverges or has poles. In the case of free electrons, you have the imaginary part of the self energy to be zero, and as a result, you have a well-defined Fermi surface. Okay, so basically you've filled up all of these states inside with electrons. Then you slowly turn up interactions, and then for weak enough interactions, you have self energy in which the imaginary part of the self energy goes as omega square. And when it goes as omega square, you can show that basically the Fermi surface is still well defined. That is, it's still reasonably sharp with some finite width, but that width is quite narrow. It's proportional to omega square. And then you can continue to crank up the interactions. You have an intermediate state, which is typically called as the marginal Fermi liquid, where the imaginary part of the self energy is linear in omega. And in such a case, well, you'll see that the Fermi surface starts to smear out quite a bit. Okay, and if you, for example, do an experiment like ARPAS, you will see that the coherence peaks are very broad.
Can I just object for a second?
Yes.
When the marginal Fermi liquid appeared in 1988, Kevin Bedell and Simanyi published a paper 2 weeks later saying Fermi liquids are like pregnancy. You're either pregnant or non-pregnant. You cannot be marginally pregnant. The issue is this is not a theoretical statement. This is a very pragmatic statement that may not even be true experimentally. But there's no theoretical support for the existence of marginal Fermi liquid.
Sure. Well, but
no, I'm not sure. I mean, you cannot quote this as something that exists. You know, it's a dream. It's virtual.
Okay, but I get your point. But I think it's still fair to say that there are certain situations where when you extract the imaginary part of the self-energy, its dependence on frequency is linear.
When you're sufficiently crude, yes. When you're sufficiently precise, no. We are working on it.
I see. Okay, sure. So let's say
I refer to imperfect experiments, you know, making these statements.
Okay. Thank you.
Likely you don't need it, you know, but.
Okay. Now, in principle, I can crank up the interactions even more, like make my interaction so large that the self-energy goes to infinity. Okay. In such a case, what you end up with is a contour not of poles, but a contour of zeros. Okay, so on this entire contour, the Green's function is not infinity, but it's actually a zero. And so this is what typically one calls a Luttinger surface, which is contour of zeros of the single particle Green's function, which arises from some infinity in the self-energy. And one of the properties of the Luttinger surface is that for example, if you plot the real part of the Green's function, you have spectral weights both above and below the chemical potential in such a way that the spectral weights contribution from below and above the chemical potential cancel exactly so that the real part of the Green's function is zero. That's one of the properties of the Luttinger surface. Now, so in the case of a Fermi liquid, the Fermi surface plays a very important role. And that is, you can think about different kinds of orders such as superconductivity, spin density waves, charge density waves, so on and so forth, as something which arises from an instability of the Fermi surface. So there is some thermodynamic quantity that diverges at some critical point that results in an ordered phase. And so that would be an instability of the Fermi surface. The question I want to ask in this talk is whether or not it's possible to study the problem of an instability of a Luttinger surface. Okay. Now, a priori, that problem may not even be well defined simply because, well, you have infinite interactions, you do not have a Fermi surface. And so, well, how do you do a proper control calculation? And it's in principle not a well-defined problem simply because you do not even know what the underlying degrees of freedom are, which are responsible for, let's say, Cooper pairing. And so that's a problem. How would you define an instability of the Luttinger surface? So the perspective that I'll take in this talk is slightly more phenomenological, but I'll tell you that this phenomenology that I'm trying to propose can be rooted in very good microscopic models. And I will come to that at the very end. But for now, the way I will attack this problem is to study the problem of, to study the pair susceptibility on a Luttinger surface, and I'll study the properties of this pair susceptibility in different regimes. And I'll show that in principle, instabilities of the Luttinger surface can still be well defined. Okay, so that's.
I have one question.
Yes.
Could you also consider Pomeranchuk type instabilities of Luttinger surfaces?
Yes, in principle you can. All you need is some sort of, so in this particular model, I'll not be considering any non-local form factors. But in principle, it's possible to consider certain types of Luttinger surfaces that are maybe having certain form factors in momentum space in such a way that you can give rise to some anisotropic instabilities. But in this talk, I'm just considering superconducting instability, but you're right. In principle, it's possible to generalize this to other types of instabilities.
Okay, thank you.
Okay, so I will now want to choose a very specific model for a Luttinger surface. It's a very simple model, but it can tell you a lot of things. So let's look at some simple models for a Luttinger surface. Okay, so the first proposal for these types of self-energies, where the self-energies are divergent, was studied some time ago, but the analytic properties of self-energies was first studied by Luttinger in 1961. And what he studied was some sort of a spectral representation of the self-energy. So essentially, he had some sigma of z, which is probably some constant with some spectral residues, sigma I, and it's really a summation of certain simple poles, okay? And in general, it's always possible to do this for a self-energy. In simple cases, such as a Fermi liquid, all of these simple poles simply act in such a way that the total self-energy is regular. So sigma is a regular function for a Fermi liquid. However, it is not necessary that these poles all cancel out to give you a good, nice looking regular function. And in principle, it's possible that maybe some of these poles are just remnant and they remain in the final equation for sigma. So it's not necessarily the case. Generally, that's the case, it's regular, but not necessarily. And to give you very specific examples, at least first at the phenomenological level, you can do this both at a microscopic level. So there are two ways you can look at this. So phenomenologically, you have early studies by Yang, Rice, and Zhang. Which I'll call for short YRZ, where they studied properties of having a self-energy which is divergent. And what they did is they used some ansatz for the Green's function. And they were able to explain a whole variety of phenomenology, such as the presence of Fermi arcs, the spectral properties in the cuprates, and also the presence or absence of the Luttinger's theorem in the cuprates, and so on and so forth. And they were able to basically study the different parts of the cuprate phase diagram using this YRZ model. And I'll get to what exactly it is. But you can keep in mind that in principle, it's also possible to write a microscopic model which can host a Luttinger surface. And the simplest such model was proposed by not a very popular paper yet, but it was proposed long time ago by Hatsugai and Kohomoto back in 1992. I will, if I have time, I'll try to talk about the microscopic model at the very end. But for now, keep in mind that whatever phenomenology that I'm going to describe today is applicable to this microscopic model in the presence of some sort of a pairing term. Okay, so what is the YRZ model which I'll be using? The simplest version of this is that you have a Green's function where sigma has a simple pole. Okay, so essentially what this does, it takes the original non-interacting Fermi surface and converts it into a surface of zeros, exactly at the pole of the self-energy. So the Fermi surface is converted into a Luttinger surface. So this is the simplest version of the YRZ Green's function. Okay, so this will be the model that I'll use. And as I said, in principle, it's possible to take the microscopic model that I'll show you at the end and come up with the exact same physics that I'm going to talk about today. Okay, so just to give you a summary of the talk, what I'll be showing is that I'll start from a model Luttinger surface obtained from the YRZ. And what I'll do is I will calculate the pair susceptibility in the same way that one evaluates the pair susceptibility to obtain the superconducting transition temperature in a non-interacting model, like the BCS model. Now that seems like a big stretch because this is a complicated, strongly interacting model. Okay, and I'll try to justify why this is possible at the very end by including all the possible vertex diagrams. Okay, but I'll take the simple approach where one can use the pair susceptibility approach that one typically does for a BCS case. And I will show that in the presence of an attractive interaction, the pair susceptibility diverges, and what you obtain is a superconductor, which is a little bit different. And that is at t equal to 0, you have a quantum phase transition from a superconductor to a state of matter, which is, in quotes, can be called as a non-Fermi liquid. Okay, so I'm going to take a Luttinger surface, I'll add this interaction, and I'll obtain a superconductor, a strongly coupled superconductor. And on top of that, what I'll study is I will study fluctuations of the superconducting states, fluctuations of the order parameter very close to the superconducting state, but out of the superconducting phase itself. And for that, there is well-known mathematical technology that helps you do that, and that is the technology that was put forward by Larkin and Varlamov. So I'll describe that in a little bit more detail later. But I will use this theory of fluctuations by Larkin and Varlamov on top of this superconducting state that I just obtained. And I will try to convince you that this model is the SYK model up to some factors. Okay. Now, as I said, we do not know what the underlying electronic degrees of freedom are, in the sense that we do not know what is forming the Cooper pair. So to some extent, this is phenomenology. But if it's in principle possible to apply the same arguments to a microscopic model by Hatsugaya and Komodo. Okay, so most of you, as you know, the SYK model, why is this important? The SYK model is known to have a dual to a model called ADS2 cross S2, which is a model of 2D gravity, which would then mean that studying the model of pairing, or studying the problem of pairing instability on a Luttinger surface and studying the fluctuations of this model would also probably have this equivalent of an ADS2 cross S2. And it's strongly suggested that we find what this model is. Although I will not talk about what the exact gravity dual is in this talk. So what I'll do now is I'll give a very quick summary of the SYK model and all the important features that are important, that are crucial for this talk. So I'll first start with the SYK model, just a brief introduction. And I will then go on to fluctuations and I'll give you the main results. Okay, for some reason this is stuck. Okay. All right, so just a quick summary of the SYK model. So the SYK model is simply a model of n Majorana fermions which are represented by some psi I, which are, we can think of them as some n bar, some matrices which are n in number, so I goes from 1 to n. And the most important thing is that these matrices have the following anti-commutation relation. And each of these matrices are L by L, where L equals 2 to the power n by 2, which is the dimensionality of the Hilbert space. The interacting part of the Hamiltonian in the SYK is given by the following 4 fermion term. And the 4 fermion term, in principle, you can write any number of fermions, but this is what they call the Q equal to 4 SYK model. And the important thing is that these J, I, J, K, L are random numbers in such a way that the average value of these random numbers is 0, but the mean square average is some finite number. Okay, so this is the basic model, and it was shown by Kitaev and Maldacena and Stanford that this model is dual to in the strong coupling limit. That is, you take the limit where beta j and n tend to infinity. In this limit, they showed that the SYK model is same as the model of 1 plus 1 dimensional gravity at the boundary as a function of time. Just to recall what the main results are, one can in principle calculate what the partition function is in the SYK model. Where this h is basically, you exponentiate this random matrix to some sort of average and introduce collective fields G and sigma by doing a Hubbard-Stratanovich transformation for the partition function. And what you end up with is a set of self-consistent equations for the saddle point given by the following 2 equations. Okay, so G and sigma are basically the collective fields that come from some decoupling of the partition function. And you solve for the saddle point solutions G star and sigma star cell consistently. And you substitute back this G star and sigma star back into the partition function, obtain the on-shell action and study fluctuations of the model about these saddle point solutions. Okay? And from that, you can calculate any number of properties, thermodynamic properties like partition function, the free energy, entropy, and whatnot. So what I'll do is, at this point, I will just give you the final results of this entire calculation in the SYK model. So as I said, this is done at in the limit where n tends to infinity, which means that you have a leading order contribution coming from n, and then you have subleading terms, which is order 1 and order 1 over n, so on and so forth, coming from the fluctuations. So in this talk, given that we are studying the problem of fluctuations about the superconducting state, what we are interested in mostly is the order 1 contribution to the free energy in the SYK model. So just to recall, the order 1 contribution in the SYK model for the free energy is simply some constant beta j minus 3/2 log beta j. So this is the order 1, and you can also calculate the order n, which will not be important for this talk simply because we are mainly mapping the fluctuations of the two models to each other. So you have the order n contribution to be log z equals minus beta E0, where C is some specific heat and S0 is the entropy. All of these quantities, E0, S0, and C, are quantities that are proportional to n. So that's why this is order n. And there is no n coming into the free energy contribution at order 1. Oops, sorry. Okay, now, if you look at the spectral density or the density of states coming from a Laplace transform of this free energy, you'll see that the leading contribution to the spectral density is a constant at low energy. So these are the two equations that I want you to keep in mind. So basically what was done, you have the SYK model, and then you study the saddle point solutions of the SYK model, and you look at the leading order contributions of the fluctuations to the saddle point. And the leading order contributions to the saddle point have this particular form as a function of beta j in the limit. This is all in the limit that beta j is much, much larger than 1. Okay? All right, I will revisit this again, but for now, I will, given that I've given you a basic introduction of what you need to know about the SYK model, I will briefly recall the theory of fluctuations in superconductors. So this was first proposed or first studied deeply by Larkin and Barlow. For a reference, you can look at their book, which was published in 2005. Okay, so what is this whole issue of fluctuations in superconductors? So typically, what happens is in a plain vanilla BCS type model, what you have is, as a function of temperature, at some critical value of T, you enter the superconducting state from a normal metal. okay? But in principle, this need not be the case. That is, when you include various fluctuation effects in the superconductor, some of the properties of the superconductor can spill over into the normal state. Or in other words, there could be a small region in temperature over which, even though you're in the normal state, some of the properties of the superconductor can be inherited. Okay? Now, in fact, it may also happen that the fluctuation effects are not seen not just close to TC, but it can happen even at temperatures that are much far away from TC. Now, what does that mean in terms of experiments? What that means is you have several variables, for example, the density of states.
I have a question.
Yes.
So there's an asymmetry in that diagram where there's a, if you like, a spillage of the superconducting state into the normal. But if I'm below the transition temperature, is there any equivalent spillage of normal into superconducting?
Well, in principle, yes, it's true. Even in the, you can also consider the case where the effects of the normal state have experimental consequence to the superconductor close to TC but below TC. Yeah, but right now, the theory that I'm going to map to the SYK model is what is the effective theory of fluctuations slightly above TC or slightly above the superconducting state. So I'm not going to worry about what happens here right now, but exactly what happens out of the superconducting state. But you're right that in principle, you can have effects of the normal state also carry over to the superconductor. Was that?
Yeah, thank you. Sorry, I had to run. Someone knocked on the door. I had to run.
Oh, okay, okay. All right. So experimentally, what happens is, for example, even though you're not in the superconducting, in the fully formed superconducting state, you will see that you will have some sort of a suppression of the density of states, which some people call the pseudogap, but it's not quite the pseudogap. But you'll see that the density of states is slightly suppressed, although not as much as what you would obtain deep in the superconducting state, which is this. Similarly, if you look at a quantity such as the specific heat, you will find that without fluctuations, you'll have a sharp jump in CV over T as a function of T at TC. But the moment you include fluctuations, you'll see that this peak is very broad. So some of these thermodynamic effects and electronic effects have been very well documented in this book by Larkin and Varlamov. So if you guys are interested in studying the theory of fluctuations about T equal to TC, that's a good reference for you to look at. Now, mathematically, the fundamental object which is studied to evaluate all of these quantities is what's called the fluctuation propagator. Diagrammatically is defined in the following way. So this is some sort of a self-consistent equation for the wavy line, which is simply L, or the fluctuation propagator. And in principle, you'll have some sort of vertex corrections always. So this is some sort of a Bethe-Salpeter equation for L. And this vertex correction could be anything. It could be coming from impurities, it could be coming from interactions and whatnot. If you're considering fluctuations of the simple BCS theory, in the absence of impurities, you can just have some non-interacting Green's function, G0. And you would have no vertex corrections. But typically that's not the case. You have impurities, you have some interactions, so on and so forth, and then in which case you would have to solve the full Bethe-Salpeter equation. Okay, just to give you a feel for what the fluctuation propagator does, one of the main use is with the knowledge of the fluctuation propagator, you can calculate all of these thermodynamic and electronic properties that I told you about before. In principle, you can also calculate what the instability temperature is, or the contour of instability is, by simply looking at the temperature at which the long wavelength static limit of the fluctuation propagator diverges. That is, you take L inverse plus pi. Pi here is basically describing this bubble. So this is pi. And you ask, what is the temperature at which this goes to 0? And what you end up with is, you can evaluate what this bubble is in this limit, and you'll find that it is some density of states times some digamma function. Which depends on Tc. And you solve the equation for Tc in the limit of large omega d. So omega d here is some cutoff. It could be phonons, it could be spin fluctuations, whatnot. And then you can solve for Tc, and in the limit of large omega d, you will find that this Tc is basically the BCS formula, where nu is the density of states. Okay, so this is at least the minimal thing that you can do with the fluctuation propagator. Okay, so that's the basic introduction to fluctuation superconductivity and what you need to know for this talk. Okay, so what I'll do now, so I told you about the SYK model, I told you about the Luttinger surfaces, I told you about fluctuations. What I'll do now is I'll simply combine the two. Okay, how do I do that? Very simple. I'll do something very naive, but I'll justify later why this holds. The naivest thing I can do is simply replace this G0 with the YRZ Green's function. Okay, so this is the crucial step. If you guys have an objection to this, we can talk about it right now. Okay, in principle, you need to make sure you have to do this in a way that respects the word identity. Okay, and I'll come to that later. But for now, I will just replace G0 with the fully interacting YRZ Green's function. And I can evaluate that. I'll show you a few steps about how that is done, and then I'll show you the final result. So this pi now is given by some integral I, where I where G is the full YRZ Green's function. Okay, in principle, you have a vertex here, and I'll come back to what this vertex is, but for now, I'll just put it to 1, and I'll see what effect that has. Okay, so I'll tell you one intermediate step, which is crucial for later discussions, and that is I will solve this in the limit where the momentum, the energy scale associated with the momentum is much smaller than U. Remember that U here is a residue of the pole. So this is U. Okay, so it's basically the residue of the self-energy pole. Okay, so what happens if you expand the fluctuation propagator? You will find that it takes the following form. In the static limits, we have some interaction minus G inverse plus pi 0. Where pi 0 can be broken up and this separation into terms that are proportional to U square and not proportional to U square is crucial, and I'll tell you why. Where S nu is simply beta inverse Matsubara summation nu over 2, where nu is some odd integer. So this is the basic formula for the fluctuation propagator without the Matsubara sum. The important thing to note here is that each of these pair susceptibilities to a given order have contributions from a term that is independent of U, or sorry, is not, well, it's depending on U, but it doesn't have a U squared coefficient, versus a term that is proportional to U squared. Okay, I can do the sum exactly. S1 is a divergent sum, so I need to put a cutoff, and I'll call the cutoff lambda, or big lambda. And I will solve this in the limit where lambda is much, much larger than U is much, much larger than temperature. Okay, remember that lambda here is the cutoff for S1 because S1 is a divergent sum. What you'll get is the following expression for L inverse. Nu again, here is the density of states at the Fermi level of the non-interacting system. We get a log lambda over U where R is simply a constant that's proportional to Q. So I'm looking for some sort of an instability now. How do I get an instability? I need to look for, so this depends on Q. Oops. I need to, when I look for an instability, what I need to do is, I need to look for the limit where Q tends to 0 and omega equal to 0. And I equate this to 0, in which case I lose this term. So this is 0. And I'm looking at the case at very low temperatures or even T equal to 0, where kappa here is beta U, okay? So if I'm looking at the limit where beta tends to infinity, then e to the power minus kappa goes to 0. So this is 0, this is 0. And what you're left with is a critical value of U, which I call UC infinity, corresponding to beta equal to infinity, where you have a superconducting instability. So this would be a quantum critical point. That is, if your value of U is larger than UC infinity, you're not in the superconducting state, so no superconductor. However, if U is less than UC infinity, you have a superconductor. Okay. So in other words, if you plot U versus T, there is a critical value UC infinity below which you have a superconductor. You can also solve this in the weak coupling limit, which I'll not show you right now, but you can show that this curve closes and you have a TC0, and this is a weak coupling superconductor. But right now we are interested in this region right here. So this is the superconducting state. What we're interested in is this region right here. We are very close to the superconducting state, and we are studying the properties of fluctuations in this tiny region above UC infinity, but at t equal to 0. Okay, one simple thing I can do right now is I can look at what happens to this fluctuation propagator at finite but low temperatures and at U equal to UC infinity. So that is, I'm looking at L inverse, Q tends to 0, at U equal to UC infinity. And what I find is some expression that looks very similar to a conformal type propagator, but not quite, because you have, okay, basically what is this expression? You have some product of a polynomial function in beta u times an exponential in beta u. Okay? Now, if you had a perfectly conformal propagator, what you'd have is this particular term, instead of having a power of 1/2, it would have a power of -1/2. Okay, it looks very similar, but not quite. Okay, so this is the fluctuation. This is the fluctuation propagator close to the quantum critical point at finite temperatures. From this, I can calculate what the fluctuation free energy is, and it turns out that the fluctuation free energy where gamma is equal to 1/2. Okay, so this must remind you of something, and that is the formula that I showed you for the SYK model. So if you look at the order 1 contribution of the SYK model, you see that I have replaced, if I simply replace J with UC infinity, which is the quantum critical point, with J, and I have a slightly different coefficient here. That is, instead of having a -3/2 in the SYK model, I have a -1/2. But apart from that, if you look at the form of this fluctuation contribution to the free energy, they're exactly the same. Okay. So from this, one can also calculate what the density of states or the spectral density is. And it turns out that in this particular case, the spectral density goes as 1/square of epsilon. Okay, so there's, at low energies, there is some sort of a divergence of the density of states. This is as opposed to the exact SYK model, which showed that rho of epsilon is a constant. And the reason there is this difference in the density of states is entirely due to the difference in this prefactor between the SYK models and the Luttinger surface model. Okay, so this is one of the main statements of the talk. Now, one of the things I didn't do is I did not include vertex corrections, if you remember, and it's important to include vertex corrections, and the reason is that the the YRZ function by itself with a vertex equal to 1 does not satisfy the Ward identity. But in the case of the YRZ model, doing that is quite simple. That's simply because we know exactly what the self-energy is. So in principle, it's possible to satisfy the Ward identity by taking into account this exact form of the self-energy. And the way you do that is simply by writing out the Ward identity and from this, given that I know exactly what G inverse is, that is, I know what these expressions are, I can back calculate what gamma is, which is my vertex correction. Note that the importance of the Ward identity is that the moment you know or restrict, the moment you know what the self-energy of the model is, you need to include the exact same diagrams to evaluate the vertex, the exact vertex. So in that sense, the vertex is constrained by the self-energy. Okay, so for the pair susceptibility, all I need is the gamma 0 vertex. And if you do that, you'll see that the gamma 0 vertex is some non-interacting vertex gamma 0, which in this case is 1 times 1 plus u squared times products of the non-interacting Green's functions at two different momenta separated by the momentum transfer q. So this is the exact expression for the vertex. And there are no more corrections. Okay, there is nothing more to do. Now, if you include this into the pair susceptibility, that is the diagram you would want to calculate, is the following. Okay, so what I've done here is I've taken the bare pair susceptibility. This is a vertex correction, and the total vertex is simply the sum of the bare vertex or the bare susceptibility plus this correction term, where the dashed lines are the non-interacting Green's functions. That is, these are the non-interacting Green's functions, and the solid line is the fully interacting Green's function. Okay, and this is exact. There is nothing more I need to add. So there is no dot dot or anything. And the reason you have this exact expression for the vertex is simply because of the simple form of the self-energy that you have in the YRZ Green's function. Okay, so I can use this to evaluate the pair susceptibility, the corrected pair susceptibility. And what you'll find is, I'm just going to copy this here. You'll find that the corrections that are coming from the vertex exactly cancel out the u squared contributions that were appearing at each order in pi 0, pi squared, pi 4, and so on and so forth. Okay, so all you're left with is the contributions that come from the first terms that do not have the u squared coefficient in the sums. So this is the effect of the vertex correction. So when you do this, when you go ahead and do this, you will find that the total fluctuation propagator, L inverse, in the long wavelength limit okay? So this is exactly the conformal propagator that you get in the SYK model. And in the SYK model, what they call it is the particle hole asymmetric case. And they have this quantity called delta, which is simply 1 over Q. Q here, if you remember, is the Q body interaction that is present in the SYK model. And when Q is equal to 4, which is the Q is equal to 4 SYK model that I showed you before, you get the exact same conformal propagator that you get in the that I showed you here. That is the effective theory of fluctuations about a Luttinger surface close to the quantum critical point. Okay. From this, you can actually calculate again what the rho of omega is. And it turns out that for the case of the Luttinger surface model, and when you consider only the long wavelength limit, rho of omega at small frequencies goes as 1 over omega. So it's more divergent than what you would have had without vertex corrections. So essentially what you can do is, with the inclusion of these vertex corrections, you can plot the full phase diagram. So you have a U versus T. At finite temperatures, you will see that with the inclusions of the vertex corrections, the curvature of this contour is negative. As a result, it goes down. And I did not talk to you about the case where you can also solve the problem in the weak coupling limit, and you can actually do that, and you'll see that it basically closes the space diagram. So you have some critical temperature at U equal to 0, TC 0. So this is a superconductor. This region here is the Fermi liquid because U is equal to 0. And this region here is the non-Fermi liquid. Okay? Which means that the superconductor that is close to the non-Fermi liquid is a strong coupling superconductor. And this would be a weak coupling superconductor. Okay, so that's the basic punchline of the talk. That is, you start with a Luttinger surface that is basically a contour of zeros of the Green's function. And in some very hand-wavy way, you define a pairing instability. And the pairing instability is basically obtained by looking at the pair susceptibility and calculating what the fluctuation propagator is. And you look for where the fluctuation propagator diverges, and you define, and you find that there's a quantum critical point, unlike the weak coupling case where there's always a zero temperature superconducting state in the presence of an attractive interaction. And if you're close enough to this quantum critical point, slightly outside the superconductor, and you look at how the fluctuations behave, the effective theory of fluctuations close to this quantum critical point is exactly the same or very similar to the SYK model. Okay, this begs the question: can one come up with a model of gravity that can also equivalently describe fluctuations in this strongly coupled non-Fermi liquid state? I don't know the answer to the question, and the reason is because I'm not an expert in gravity. Maybe some of you will have more insights, and I'm happy to talk to you guys. The one last thing I want to mention is, as I promised you, there is a microscopic model which gives you a well-defined Luttinger surface, and that was the model by Hatsukai and Kuromoto. Maybe in the future, I'll have some time to talk to you about this as well, but for now, I'll just tell you what the model is. So you have very simple hopping term that you see with chemical potential. And you have a Hubbard-like interaction except that this Hubbard-like interaction is constrained. And the way it is constrained is that you only consider scattering between electrons which satisfy the center of mass momentum, the center of mass position constraint. That is, only electrons which, only scattering processes which conserve the center of mass are included. In the scattering process. So that is constrained by this delta function. It turns out that this model can be exactly solved. And if you add a pairing term.
I mean, sorry about it, but it's misleading. What you basically say there is that you have just an index in U acting on momentum eigenstates, right? So it's nk up, nk down.
Yes, that's right.
Right, and saying this way, you know, you make way too much out of it. It's a very cheap, but very fascinating and interesting thing, that by having the Herbert interaction acting momentum space, you keep your momentum eigen states, but you work in Mottness. It's true, yeah, that's correct. I find it strictly illegal to sell it this way, because you suggest something which is not there. It's a very, you know, cheap and easy thing to do.
Well, but the point I'm trying to make is, well...
Yeah, the point I'm trying to make is you try to sell something that's entirely trivial in a way that it looks more interesting than it is. You just write the nk up, nk down with a u in front of it. That's it.
Yes, but if you Fourier transform this term, that's exactly what...
I know. But when you, you know, sell the Herbert model in a way that you do a long story momentum space, and you write it in C dagger K and C dagger K plus Q's, it looks more than it is. It's just a silly contact interaction in real space. This is a contact interaction momentum space.
Okay.
I talk about honesty.
Yes.
This is not honest.
Well, I don't know why, because if I Fourier transform this, you get...
No, because you suggest to the audience that it's more profound than it is. It is very unprofound. It's mathematical construction, completely trivial.
I don't think so, because if you, the simple matter of fact is this, okay? This model gives you a Luttinger surface just as a type of the YRZ. That's my point.
Okay, mathematics, not interpretations. Mathematically, it's trivial.
Okay. Do you agree with the statement?
Don't argue about it, you know?
No, you agree with the statement, right? You agree with the statement that this model has a...
You know, we have standards here.
Okay. Well, my statement is that this model has a Luttinger surface of the same form that is of the YRZ type. And in principle, if you look at the paper, you'll see that the Green's function has a self-energy with a simple pole. And the simple pole in the self-energy is responsible for giving rise to a Luttinger surface. And if you study the pairing instability of a Luttinger surface, you get the exact same physics that I'm talking about. Well, okay, so that's the end of my talk. If you guys have any questions, I'm happy to take it.
Thanks a lot, Chan, for the talk.
And I'm happy to hear more from Jan if he has more. I mean, I still don't understand what his objection was towards the end, but I'm happy to hear him out. So
yeah, no, I have not too much to say. You know, it's basic presentation because I think that this HK model is quite interesting. Worrying about Luttinger surfaces is quite interesting. I just object against, you know, it's pompous, you know, to sell it as if it's, you know, mathematically very profound and you have to sit down for hours. Excuse me, it's a very simple counting exercise, right? When you start out with HK, use a momentum space, the single particle momentum constant numbers are perfect because your interaction is commuting with it, right? You just count it out. And it's actually interesting because of its simplicity. Let's say your former boss, Philip, is sort of selling this. It looks like SYK. And it's horrible, you know, because in SYK, this non-locality is...
So this model itself is not the SYK. That I agree.
Yes, agreed, yeah.
I agree with you. But my point is, this model has a Luttinger surface, that's all. Do you agree to that?
I agree. It's interesting.
If
Yeah.
you agree that the model has a Luttinger surface, and if you agree with my arguments that I gave you right now, I'm happy with that. I have nothing.
You know, we are in that regard friends. It's a very interesting model. It's worthwhile to look at it. I myself have been obsessing about it. It's all fine. Just against the way of presenting it. Always presented this as, you know, mathematically it's trivial. It is.
Yeah, I agree with you that.
And that's
I
good.
agree with you that the model is a little bit more simplified compared to the. So there is nothing profound about the model. I agree.
Yeah.
The model itself is not very profound, but
what it means is interesting, right?
it is interesting. But if you study the problem of fluctuations on top of this model, that's where the interesting things comes in.
Yeah, absolutely. We agree.
Okay.
We agree.
If you agree to that, we have no objections.
Same page. I mean, I may actually add a bit of a comment to it.
Okay.
But I see it differently. Where to start? It's talking to experiment in a way. And in the experiments of relevance are the overdose cuprates. And in the overdose cuprates, there are really quite good evidence for the presence of a Fermi surface. But that Fermi surface is actually violating the Luttinger theorem. And even worse, there's this business with Ivan Bošević with extremely low superfluid density, really a conundrum. When you say that you have a good Fermi liquid and a momentum is quite well defined, right? So the impurity scattering is not a big deal. It's actually quite clean, you know, when you go in these Bošević samples, resistivity is not a big deal, blah, blah. Then it should be, right, that the superfluid density and the normal density should be the same thing in essence. Right, yeah. And the finding is that superfluid density is obscenely small compared to what you expect.
Yes.
Yeah, you know about Philip, right, who sort of extended this paper a bit, demonstrating, right, that you call it Leggett counting, whatsoever, Luttinger counting, both of them are completely different. Also in this HK, I like to call it HK method, right, to avoid learning these Japanese names by heart. And it's more like you think about the Fermi liquid, and what you do in the Fermi liquid is you have a fixed point, and the fixed point is the Fermi gas. In the Fermi gas, you have your perfect momentum state, you have your perfect Fermi surface, right? You have your perfect Fermi C, you start counting there, right? And there you get the Luttinger theorem automatically. And then it's very continuous. You can adiabatically continue this to a strongly interacting case, right? And as long as the Paul strength is finite at the Fermi surface, you know that things like the Luttinger volume theorem and the Leggett theorem are still completely true. Now you look in the cuprates, you have a Fermi surface, but this Fermi surface is violating Luttinger and it's violating Leggett. So you cannot possibly use your Fermi gas as fixed point. But now you can say, okay, I take this HK Hamiltonian, this weird attitude, there are still interactions that don't destroy single particle momentum. Right? So W occupying states in momentum space is hit by Mottness, by the fact that you cannot put two electrons in the same momentum state phase. You count everything differently. Right? And that automatically violates a Luttinger and automatically violates a Leggett. In other words, could it be that this overdose cuprate Fermi surface type state is actually an adiabatic continuity from an HK-like reference state? You see, it's very intriguing, it's very interesting.
Yes.
And then you can worry about the productivity, blah, blah. I agree at the moment you add extra interactions, a whole new universe opens up. So I think it's very interesting. Yes.
But I realized that the HK model, it just looks so simple and it's very misleading. If you just by itself, it looks very simple.
Yeah,
But
but
if
the
you
Fermi gas is
study
very
some instability on top of it, it just becomes very weird.
yeah,
And
but
I'm exploring this more in
doing
detail.
this
But
thing, you know, there's the power.
yeah, yeah, absolutely,
You
absolutely.
need and so the reference point of your independent continuity that gets the counting right. While at the same time, there's a Fermi surface. I mean,
Yeah,
if it's a state that's really not a Fermi surface, you will never discover, not a Fermi liquid, you will never discover a Fermi surface. And you
yeah,
now need sort of this intermediate thing, right, that cannot be counted from a Fermi gas, but still has a Fermi surface.
yes.
Right? I like to, I mean, people tend to not quite appreciate it, but take the helium-3 Fermi liquid. It's an absurd example, right? So helium-3 is about the best Fermi liquid we know. It's doing everything impeccable when it comes to Fermi liquid. But you have to realize that it starts with a UV, where the liquid behaves like a van der Waals liquid, right? So basically you have these hard balls, helium atoms that touch each other, forming a nearly close-packed solid, right? And here and there, there's a defect and something can move there.
Mhm.
That's your UV starting point. And then, weirdly, it renormalizes in something, right, that can be in turn continued to the perfect Fermi gas. Right? The Fermi liquid is just the continuation of the Fermi gas.
Right.
Weird things can go on in that continuation process that we don't understand at all. So why shouldn't we exclude the possibility that you depart from that weird local in momentum space interaction, right? That then eventually becomes bigger than life at a fixed point. Although the real system is, of course, completely different from that.
Right.
And it's basically sort of driving this point to the very end.
So Philip has this paper, recent paper. I don't know if Philip Phillips, he studied this in a little bit more detail, and the claim is that they understand some of the basic microscopic ingredients. So they have this whole ounce versus double ounce pairing to give rise to superconductivity, and that comes directly. So the difference between this and that is that if you look at the SYK model, you find that there are two bands. One is the upper Hubbard band and the lower Hubbard band. And there, if you place the chemical potential in one of these bands, you get that exotic physics that these people propose.
Yep.
And in order to get the physics that I'm talking about here, what you need to do is take your chemical potential and put it right below the upper Hubbard band. And you get a fully formed Luttinger surface, and you get a quantum critical point.
Yeah.
On the other hand, if you put your chemical potential in one of the bands, you'll see that the quantum critical point is avoided.
Yeah.
And you get the, I mean, it's still interesting.
Phase, right?
Yeah. And the moment you are in the right between the bands, you get a fully formed Luttinger surface, and your quantum critical point can never be avoided. And all of the physics that I'm talking about now follows automatically in that limit.
Yeah.
So that's something I want to explore a little bit more, and probably collaborating with these people, and we'll see how that goes.
That's my sense, right? That it looks very innocent, but at the moment you start to do computation, you add interactions, that there's a whole big zoo of interesting alleys to. I appreciate your talk. I'm familiar to Philip's story, and
Thank you.
it's a different story. Yeah. I'm not so sure whether right. It really relates to holography. I mean, holography. When it comes to Mottness, it's still very experimental, right?
Right.
And the sort of basic counting, it's not quite the easy thing to do in holography.
No, but the issue is, one thing that can be done is simply look at the equivalent model in holography. So, for example, whatever little holography I know that. This,
there's a general problem, and my general problem is that SYK is completely overhyped. I don't agree that when you see SYK, it thinks that you have really a relationship with holography. And when you look in Super's heart, I know he has a lot of doubts there.
So you're saying you don't agree with that?
Yeah.
I see.
But so one thing is sort of recognize SYK like things. Another thing is to say, oh, now I have a straight connection to holography. Forget about it. It's very obscure.
Okay, so that's something I would not have a comment upon because I do not know what it is. If that's a connection that is shaky, then I'm not sure.
Yeah, it's not true, you know, that anything has been proven about the relationship between SYK and the isomorphism, say, in 4 or 5 bulk dimensions. Just not true.
Okay.
Okay, guys. We have more questions.
I've actually to move on. I enjoyed your talk.
Okay.
I'm happy. Actually, this discussion also tied up with nicely with Philip's talk in the conference.
Okay.
Yeah, he talked about this HK model, if I'm not wrong. So, but okay, let's see if there's any other question. I mean, we are over time, but this is the advantage of the online seminars. Whomever wants to go, they can go.
So I had one other question.
Mhm.
Go ahead.
If you replace the y or z Green's function with, say, some unparticle or power law Green's function, what would you get? How would things change?
The thing with the power law Green's function is it does not have a Luttinger surface.
Mm-hmm.
In principle, if you're able to modify it in such a way that you have a power law Green's function with some arbitrary power, at the same time, you have a 0 in your propagator, then I imagine that you'll get something exotic. It's just that I don't know any such model which gives rise to a power law Green's function with a Luttinger surface. If you can come up with such a model, that would be great to explore.
Thank you.
Thanks for the question. Any other question? Otherwise, we thank you very much, Chandan, for the nice talk, for your patience, and for the effort of doing it online. And yeah, okay, you're getting virtual clapping from people.
Thank you.
Otherwise, we leave it here. The talk will be recorded and accessible on the web. Also, the slides. Well, I'll talk to you about the slides because it's not. And next week, in a week from now, we had Richard Davison from Edinburgh talking about relations between transport and chaos in holographic theories. So that's all for today. Thanks a lot, everybody. So.